Okay, so here we have some complex number z, which is equal to cos of theta plus I sine of theta. De Moivre's theorem states that z to the n is equal to cos of n theta plus I sine of n theta for all integers n. In order to prove this, we do it in 3 different steps. First, a proof for positive integers. Next, a proof for 0, and then a proof for negative integers. So first, the proof for natural numbers, we are going to use a proof by induction. So consider n equals 1. Cos theta plus I sine theta to the 1 is just equal to cos of theta plus I sine of theta. And theta is equal to 1 times theta. Therefore, the result is true for n equals 1. Now, let's assume that the result is true for n equals k. That is, that cos of theta plus I sine theta to the k is equal to cos of k theta plus I sine of k theta. Now, consider n equals k plus 1. Cos theta plus I sine theta to the k plus 1 is equal to cos theta plus I sine theta to the k multiplied by cos theta plus I sine theta. And from our assumption, we are saying this is equal to cos of k theta plus I sine of k theta multiplied by cos of theta plus I sine of theta. Okay, so if we expand this out, what we get is cos of theta multiplied by cos of k theta plus I cos theta sine k theta plus I sine theta cos k theta plus I squared sine theta sine k theta. Of course, I squared is just equal to minus 1, so this just becomes minus sine theta sine k theta. Now, if we split this into the real and imaginary components, we get that the real component is cos theta cos k theta minus sine theta sine k theta, and the imaginary is cos theta sine k theta plus sine theta cos k theta. Now, for the real part, we can see that this is just the compound angle formula for cos. So this becomes cos of theta plus k theta, or cos of k plus 1 times theta. And the imaginary component we can recognize as the compound angle formula for sine. And so this just becomes sine of theta plus k theta, or sine of k plus 1 times theta. So therefore, cos of theta plus I sine of theta to the k plus 1 is equal to cos of k plus 1 times theta plus I sine of k plus 1 times theta. Therefore, the result is true for n equals k plus 1. And by induction, as the result is true for n equals 1, the result is true for all natural numbers n. Okay, so next we have our proof for 0. So if we consider n equals 0, then we get that cos theta plus I sine theta to the 0 is equal to 1. And therefore the argument is equal to 0, which is equal to 0 times theta. Therefore the result is true for n equals 0. Finally, our proof for negative integers. So if we consider n equals minus 1, well, cos of theta plus I sine of theta to the minus 1 is equal to 1 divided by cos theta plus I sine theta. Now, to divide complex numbers, we know that we have to multiply both the numerator and the denominator by the complex conjugate of the denominator, which in this case is cos of theta minus I sine of theta. So this is what we get, and if we expand out the denominator, we get cos theta minus I sine theta divided by cos squared of theta minus I squared sine squared of theta. And because I squared is equal to minus 1, these minuses will cancel out, which will just give us cos squared of theta plus sine squared of theta on the denominator. And from our trig identities, we know that this is equal to 1, and therefore this just becomes cos theta minus I sine theta. Cos is an even function, so we know that cos of theta is equal to cos of minus theta. Sine is an odd function, so we know that sine of theta is equal to minus sine of minus theta. Now, if we substitute these into the equation above, we get that cos theta plus I sine theta to the minus 1 is equal to cos of minus theta plus I sine of minus theta. And minus theta is equal to minus 1 times theta. Therefore, the result is true for n equals minus 1. Now, if we consider n is equal to minus m, where m is a positive integer, then we can say that cos theta plus I sine theta to the minus m is equal to cos theta plus I sine theta to the m and then to the minus 1. And so for the inside of these square brackets, we can just use our proof for positive integers that we did earlier to say that we have cos of m theta plus I sine of m theta all to the minus 1. And from our proof we just did for n equals minus 1, we can say that this is going to be equal to cos of minus m theta plus I sine of minus m theta. And as minus m is equal to n, this becomes cos of n theta plus I sine of n theta. Therefore, the result is true for all negative integers, n. So we have proved it for natural numbers, we have proved it for 0, and we have proved it for negative integers. And therefore, the result is true for all integers n.